So we can say that alpha and beta are completely independent of temperatures, but gamma is actually dependent on temperature. So once the atmosphere is at 4 degrees Celsius, then the surface of the lake is also at 4 degrees Celsius. The change in temperature actually causes heat to be exchanged between the two parts. So it is known as conduction. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about some thermal properties of matter. So let's see what holds for us today. So in the previous classes, we discussed about both alpha, beta and gamma wave. Now we are going to discuss what is their dependence on temperatures actually is. So we can say that alpha and beta are completely independent of temperatures, but gamma is actually dependent on temperature. Well, in very short words, we can say that gamma is only affected by temperature in solids and in gaseous forms, while in liquid form it is also independent. But for the sake of writing, we'll write it down in bulletin points. So we can say that alpha and beta are completely independent of the temperature, while metals have more alpha value than non-metals. Obviously, because metals actually expand faster when we apply a specific amount of change in temperature to them. And gamma value for solids, example like copper or any other metal which expands like that, increases with temperature. That is, when you have a steady heat supply to a metal like copper, it increases in its dimensions, and that's why we say that gamma value for solids like copper increases with increase in temperature and becomes a constant value after hitting a higher temperature state. That is, at lower states it starts to increase, but it's not like the increasing nature or the expansion goes on forever. After some time, that expansion process stops and it reaches a constant phase. So that's why we say that at higher temperatures, gamma value becomes a constant. And gamma for liquids is again independent of temperature, and gamma for gases actually decrease with increase in temperature. So that is all about temperature and relation between alpha, beta and gamma. Now the next topic is anomalous expansion of water. So what is this anomaly? Anomaly is something that does not fit the pattern. If anything is anomalous, it means that there is a general pattern under which this particular phenomena does not fit into, or we can say that it is the odd puzzle that is standing out. So what is the anomalous expansion of water? It means that there is some anomaly about the expanding nature of water. Obviously, water expands when we apply temperature to it, right? Not exactly. Because all other things, let's say any metal or any other material, when we apply a temperature to it, we know that it expands. It is obvious, right? The volume increases, the size increases. So when we apply a temperature, automatically the size increases. But for water, it is completely different. Instead of increasing, that is, if I have a bowl of water, if I have a completely filled beaker with water and I am giving heat to that particular system, then automatically we know that, okay, yeah, water should expand and it should create water vapor after a certain point, right? But the problem is that experimentally it is found out that instead of expanding, water actually contracts at first. But sir, how is this possible? It is completely possible only from a temperature range from 0 degrees Celsius to 4 degrees Celsius. Between this particular temperature range, what happens is that instead of water just generally expanding outwards, water is actually contracting, and then after 4 degrees Celsius only, the volume is increasing, or simply the water is expanding. So this particular trend, where initially it is contracting before it is expanding, that particular anomalous nature is explained here as the anomalous expansion of water. So again, if I take, let's say, an ice cube or something. So I'll take water at 0 degrees Celsius. At 0 degrees Celsius, water and ice coexist together. But again, let's say this is a bowl of water sitting at 0 degrees Celsius. So again, water and ice will be mixed in that particular state change temperature. But again, so in this particular condition, there is already a volume existing within this particular beaker, which means that initially there is a volume. So if I take a graph between volume versus temperature, what it is observed is that initially it has a volume. Now I am going to increase the temperature on this particular system. So what we expect is that, okay, volume should increase. But instead of doing that, from 0 to 4 degrees Celsius, what happens is that the volume actually decreases first up to a certain mark, and that mark is 4 degrees Celsius. So up to 4 degrees Celsius, water actually contracts or the volume decreases and then it increases. So this particular trend of water is known as anomalous expansion of water. And this particular trend actually is a mechanism by nature itself to prevent the loss of lives. I'll explain why that happens and the way that nature saves a lot of things by just this anomalous expansion of water. So again, before that, you need to understand that, okay, this is the volume temperature graph of anomalous expansion of water. In a sentence, we can say that water contracts on heating from 0 to 4 degrees Celsius and it expands after crossing 4 degrees Celsius. And that particular phenomenon is known as anomalous expansion of water. So we saw the volume temperature graph, but there is also a possibility that the density temperature graph is also asked. So how do you define density temperature? Again, we know that density rho is equal to mass divided by volume. So mass by volume. So we just have to look at what happens to the volume. Is it going up or is it going down? Obviously, if it is decreasing, the entire density value increases. If volume is increasing, it means that density value will decrease. So whatever happened with the volume temperature graph, you just invert it and you just get the density versus temperature graph. Again, what happens is that initially it has a particular density and then the volume decreases, which means density increases. The density of water becomes more and more higher. And then after a particular point, let's say 4 degrees Celsius. So at 4 degrees Celsius, water has maximum density. And after that, what happens? Density also decreases. So that is the nature of density versus temperature graph for anomalous expansion of water. So the next topic is freezing of lakes. But sir, how does lakes freeze? Is that a new thing? That is a new thing for you because in extreme conditions, let's say north of Europe or close to the polar regions, the lakes, especially in the European countries, actually freeze over during winter times. But what's so special about that? The special thing about that is that in this particular lakes, there is a huge variety of aquatic life, including plants, fishes, that is different species of fish and frogs, eels, many creatures are there. So during the freezing over process, how does this aquatic creatures survive? Because once they freeze over, if they are also frozen, then they die. Right? Obviously, if your heart stops, you die. It's not like every animal can go into hibernation. So how do they survive? Once the lake freezes over, it's not like the entire lake is frozen like an ice cube and during the summer season, it is melted and the creatures came back to life. It's not like that. During the winter, they are still alive and they are maintaining a habitat inside that particular lake. So the problem is, how does these animals survive when the lake freezes over? So to answer that question, we have to combine the freezing of lakes and the anomalous expansion of water and squeeze them together. So what exactly happens is that during the winter time, what happens is that, okay, there is water like this in the lake. So during the winter time, the temperature actually drops. So let's say that it was initially 20 degrees in the summer and now it is coming to 20 degrees and it's night time, it's winter, it's now 5 degrees, it's 4 degrees. and exactly at 4 degrees Celsius, something happens. Before getting to that, you have to also understand that when the atmospheric temperature drops, the surface layer of the water, this surface layer of the water also becomes that particular temperature. That is, the surface layer first drops its temperature according to the atmospheric temperature. So once the atmosphere is at 4 degrees Celsius, then the surface of the lake is also at 4 degrees Celsius. Now, what is so special about 4 degrees Celsius? The 4 degree mark is the point where water is having maximum density or minimum volume. So, since water is having maximum density and minimum volume, it means that this top layer is now more denser than whatever is below that. So you do know that lesser denser objects float. So what happens? This entire layer sinks down to the bottom. That entire layer of water sinks down to the bottom and the lesser denser region rises up. And what happens? That region also gets cooled down to 4 degrees Celsius. It also becomes denser and denser and it just drops down. And the other layer drops up and again it cools down to 4 degrees Celsius and it also drops down. But there is one problem. This happens at 4 degrees Celsius, right? But what about when the atmosphere crosses 4 degrees Celsius? That is, let's say 3 degrees Celsius or 0 degrees Celsius or minus 2 degrees Celsius. What about them? See, you know that water freezes or starts to freeze at 0 degrees Celsius. So, at 0 degrees Celsius, this particular layer of water is now starting to freeze. And at minus 2 or minus 3 or minus 4 degrees Celsius, what happens is that the entire layer of water that is on the surface is now frozen. But what about the remaining part? The remaining part of the lake is not frozen. That is because at 4 degrees Celsius, water is having maximum density, which means the higher density water is actually below the surface. And anything that is above that, that is 3 degrees Celsius or 2 degrees Celsius, compared to the 4 degrees Celsius water, it is less denser. So since the water at 3 degrees or 5 degrees or 2 degrees and 7 degrees, whatever it is less denser, it floats, which means it rises to the surface. So any water or any layer of water which is below 4 degrees Celsius is actually less denser, and ice happens at, or simply the freezing process happens at 0 degrees Celsius, which means it is also less denser than the 4 degrees Celsius water. So the top layer freezes over while the bottom layer is still at 4 degrees Celsius. So this 4 degrees Celsius water is now preserved. And once the top layer of the lake freezes over completely, that particular layer acts as an insulator between the atmosphere and the inside of the lake. So technically, throughout the winter, the lake does not really freeze over. The only thing that freezes over is actually the surface. So the surface actually freezes over while the lake itself is preserving all the life using the laws of thermodynamics. Or simply, we just observed them and quoted the laws of thermodynamics. So nature has a particular way of preserving lives where it certainly have to. And this will not be possible if not for the anomalous expansion of water, which provides higher density at 4 degrees Celsius. So how can we write it in words? So in words, we can say that when atmosphere is at 4 degrees Celsius, the lake or the surface of the lake also becomes 4 degrees Celsius. And since water has maximum density at 4 degrees Celsius, this water moves to the bottom layer while the bottom layer water comes to the surface. And then the surface is again cooling, or simply we can say that atmosphere, when it reaches below 4 degrees Celsius, the surface of the lake is less than 4 degrees Celsius, and this time this water stays on top because the bottom layer is more denser. That is, water at 4 degrees is more denser. Obviously, the water which is less denser will stay at the surface only, and then this water will, as the temperature gets lower and lower, this water will freeze over, and we can see that as temperature decreases further, the surface freezes and water below that particular surface stays at 4 degrees Celsius. And without this, the entire aquatic life would be at a loss. So that is the relation between anomalous expansion of water and freezing of lakes. Now it's time to learn about a very few basics about thermodynamics. So what exactly is heat? You might say that, okay, I'm feeling very hot. Okay, the heat in this room is too much, too low. So what exactly is heat? The primary thing you have to understand is that heat is not associated to temperature. We generally say that higher temperature, higher heat, lower temperature, lower heat, like that. But in thermodynamical sense, heat is not temperature, but rather we can say that heat is simply energy in transit. That is, when energy is transferred, that particular energy is known as heat. If you're giving heat to a system, it means that you're transferring energy to a particular system, or the exchange of energy between a system and a surrounding is known as heat. It is not heat exchange. It is not heat given to a system. It is just heat, because the definition of heat itself means energy transfer. So if you say heat energy in thermodynamics, you're just saying energy transfer energy. If you're saying heat exchange, then okay, fine, sort of it is right. But you can never say heat energy in thermodynamics or simply heat transfer, because again, heat itself means that it is the energy in transit, or simply the exchange of energy between a system and a surrounding, or two systems. That particular transfer of energy, that particular energy in transit is known as heat. So in words, we can define heat as the form of energy that is transferred between a system and surrounding when there is a difference in temperature. So we can say that if system A is at, let's say, 0 degrees Celsius and system B is at, let's say, 5 degrees Celsius, there is inherently a difference in temperature. So there will be exchange of energies between these two systems, and that particular energy exchange is known as heat. And this will continue to do so until both of them are at exactly same temperature, or simply thermal equilibrium. So that is known as heat. That is simply energy in transit, or the transfer of energy between two systems or a system and a surrounding when there is a particular difference in temperature scales. And the SI unit of heat is, either you can use calorie or you have to use joules. Joules is the name of a French physicist who contributed a lot to the field of thermodynamics and the way of heat transfers. So we recognize him and kept the unit of heat as joules, and it is indicated by capital J. Or you can also use what is known as a calorie. It is the same amount of calorie you burn when you're doing an exercise. So you can also track heat, or simply use the unit calorie for heat. And the value of 1 calorie will be actually equal to the value of 1 calorie, that is 1 cal, is actually equal to 4.18 joules. So if you ever need to convert joules into calorie, you can use this particular trick. That is 1 calorie is equal to 4.18 joules. And the last thing to be noted about heat is that it is generally indicated by the capital letter Q. So if I write Q anywhere in thermodynamics, it means that I am giving heat. That is, energy is being transferred from one system to another system, or just simply I am giving energy to one system, and mostly it will be thermal energy. That is why we indicate that using Q. Why Q is because physicists have a weird way of naming certain things. That is why it is Q. We use same symbols for many constants and substitutions. So that's why we have a very odd nature of symbolizing and representing many quantities, but still Q is represented as heat. So Q is heat. Now we have to study three important variables in thermodynamics, which is quite often used in proving some theorems, and it is very important that you understand these concepts. So the first thing is specific heat capacity. So what is this specific heat capacity, and why is it so specific? It is specific because we are specifying the amount of change that is induced in that particular system due to the energy which we are providing, or we are just quantizing the energy we are giving to a particular system. So we can say that specific heat capacity is actually defined as it is the heat required or given to a system in order to raise the temperature of unit mass substance by 1 degree Celsius. So if you have a unit mass substance, let's say 1 kilogram of any substance, or 1 kilogram meter cube of water, or any substance that is of unit mass, and you're raising the temperature just by 1 degree Celsius, how much heat is required for that? How much energy do you have to input into that particular system so that the temperature only raises by 1 degree Celsius? And that is known as specific heat capacity. And again, you have a relation, that is Q is directly proportional. That is, the heat given to that particular system is directly proportional to some quantities. Obviously, what are the quantities here? There is mass and there is temperature. So again, if you give heat to a system, the temperature changes, and it also affects the mass of that particular system. So instead of giving a lot of heat, I'm going to give a small amount of heat, or simply delta Q symbolizes change, or simply a small amount of heat that is obtained by the system or given to that particular system. So delta Q will be directly proportional to M, that is mass of the system, and delta T, that is the change in temperature. So we can just say that to avoid this particular proportionality sign, we can say that delta Q will be equal to Sm delta T, and this S is known as specific heat constant, and it actually depends on the material of substance which you are using. Now we have two more things you have to understand, and that is heat capacity and molar heat capacity. Now heat capacity is very similar to specific heat capacity, but we are not specifying it for unit mass, but rather a general statement. And for molar heat capacity, it is for n number of moles of substance. So the only difference is that it will be for n number of moles, and the constant will change. Instead of S, we will use a new constant that is known as C. You don't have to study about the intricacies or where the equation came from. You only have to know the equation. So I'll just give you the equation, that is delta Q will be equal to NC delta T, where N is the number of moles of substance and C is the molar heat capacity constant. So just C is used. And in heat capacity, again, if we are not specifying, and you will get the equation as delta Q will be equal to Ms delta T. Now, why this Ms delta T? That is because heat capacity is defined as, again, we'll use capital S in order to specify heat capacity. For specific heat capacity, it is small s, and for heat capacity, it is capital S. So we'll specify heat capacity as mass times, that is mass times the specific heat capacity, small s. So heat capacity is equal to mass times specific heat capacity ms. But we already know an equation for specific heat capacity, and that is S delta T. That is why instead of ms we are writing ms delta T. So specific heat capacity is defined as unit mass of substance is raised by 1 degree Celsius, how much energy is required for that. Now, in a general sense, if you are raising just temperature of any mass, then you can say that that is heat capacity. So that is known as mass times specific heat capacity. If you have 10 kilograms of substance, then the energy required to raise the mass of 1 kilogram by 1 degree Celsius, that is a unit measurement. So specific heat capacity is actually a unit measurement. Just like we have 1 centimeter, 1 kilogram. So if you want 10 kilogram of substance, you multiply the magnitude 10 with the unit, that is 1 kilogram. So 10 into 1 kilogram is 10 kilogram. Just like that, we have specific heat capacity as a fixed unit. That is for unit substance, how much energy is required to raise the temperature by 1 degree Celsius. And heat capacity is generalizing that particular statement for every other mass. So that is why we have this particular equation. And now what is the practical use of this particular thing is that in older days, before the invention of modern day cooling agents or cooling liquids, we used to use water. That is, we used to use water in order to cool down radiators in cars. If you remember the old ambassador cars and all that, it will be piping hot. The engine will be running and it will be very hot. And in order to cool down the engine, we will pour water into the radiator. And we used water. We did not use any other things. We did not use steel balls. We did not use, let's say, tungsten. We did not use iridium. We only used water. That is because water has a very high specific heat capacity compared to other things. For example, if you take an incandescent bulb, that is the bulb which is glowing, inside that there is a small tungsten film or simply a tungsten wire. That particular wire will heat up very fast, while water only heats up very slow. When you heat up a metal, the metal heats up very fast. When you heat water, water only heats up very slowly. That particular change is because the specific heat capacity of water is comparatively very high than that of a metal. For example, we can say that if I take the two metals, let's say I'll take tungsten here, and water here. And if I ask you how much energy do I have to supply to 1 kilogram of water and 1 kilogram of tungsten just to raise its temperature by 1 degree Celsius, then it just so happens that tungsten will only require, let's say, about 180 or 200 joules of energy. 180 to 200 joules of energy maximum. But water requires around 400, approximately 4000, not 400, 4000 joules of energy just to raise its temperature by 1 degree Celsius. Which means that the more heat or simply the more energy or thermal energy you give it to the system, water still stays at that particular temperature and it only raises if it absorbs a lot of energy. So when an engine is really hot, when an automobile engine is really hot, it gives away thermal energy. That is what the heat is. So if you use water in the radiator to cool that, the water is absorbing that much amount of energy. Just to increase 1 degree Celsius, it has to absorb 4000 joules of energy. So in order to absorb that much energy, the heat of that particular engine or the temperature difference of that particular engine will go down drastically. That is why we use water in order to cool down automobile engines. Or simply we can just say that is why we use water as a coolant in cooling down certain equipments or simply as a coolant in automobile engines, other mechanical parts and all that. We use water because it has very high specific heat capacity. So the next topic is change of state. Again, you have studied this in detail in your high school, that is when temperature of a system changes, or simply when heat or energy is supplied to a system, its state actually changes. If ice receives energy, or simply if you heat up ice, then it melts and turns into water. So that is a state change from solid to liquid. Just like that, from liquid to gas and gas to solid, like these three cycles you have already studied. So what is so special about the state change? So you already know that during the state change process, the temperature remains constant. That is, at 0 degrees Celsius, water and ice coexist together. And just like that, solid liquid and liquid solid, that phase also remains. That is, both phases are also present at that particular temperature. All this you already know. But there is something you don't know, and that particular new term is that the latent heat required to change the state of unit mass of substance is given by delta Q is equal to Lm. So, in order to understand this particular statement, you need to understand what is latent heat. So, what exactly is latent heat? You know about specific heat, but what is latent heat? So, latent heat is actually the heat that is required to change the state of a system. That is, if you have an ice block, in order to change that ice block, solid to liquid, that is water, ice to water, how much energy is required in order to change, let's say, unit mass of an ice cube into water? So the energy required for that particular change is known as latent heat. So specifically, we have latent heat of fusion, we have latent heat of vaporization, like that. But generally, we can say that the heat required to change the state of a system of unit mass is known as latent heat. And it is indicated by the capital letter L. So L indicates latent heat. So the first thing we have to know is latent heat of fusion. Fusion means the molecules are sticking together, we are recombining it to form a solid. Or simply we can say that the heat that is required to change unit mass of substance, or simply solid to liquid or liquid to solid. So you're either freezing water or you're melting ice. So this particular process, the heat or simply the energy required for this particular process is known as latent heat of fusion, and it is indicated by L subscript F. And you also know that L is actually a latent heat, and we also know that Q is actually the heat that is given to the system, and M is the mass of the substance. Then we can see that delta Q, that is the small amount of heat given to a system, will be equal to LF, because it is latent heat of fusion, times M, because heat is directly proportional to mass and L is the constant which we use here for latent heat. So we have delta Q is equal to LF into M. Now we also have latent heat of vaporization. Same thing, the only difference is that instead of solid to liquid, we are converting liquid into gas. So the heat required for conversion of liquid into gas or gas into liquid is known as latent heat of vaporization. Again, the equation is given by delta Q is equal to L subscript V, because it is vaporization, times the mass of the substance that is used. And latent heat, actually, that is the constant L, actually depends on the nature of the material which you are using. If you are using a certain amount of material, let's say ice, you'll have 1 L value. If you're using tungsten, you'll have 1 L value. If you're using frozen honey, you have another value. So it depends on the nature of substance which you are using also. Now again, if I draw a graph between temperature versus state, then I can simply say that, okay, if I increase or just give heat to that particular system, let's say this is ice. So this is ice or simply solid. So in this particular system, I'm giving some heat, then automatically the temperature changes, and at 0 degrees Celsius, it becomes a mixture of ice and water. that is a mixture of solid and liquid coexisting together. So at this particular range, even though both are coexisting, two states are coexisting, the temperature is constant. So again, at 0 degrees Celsius, the temperature is constant, but two phases, that is two states, are coexisting together. And again, if I keep on increasing the temperature or just giving heat to that particular system again, then this system changes to, that is, the ice water changes to water only. And after this particular point, that is the 100-degree mark, after the 100-degree mark, what happens is that it boils and it becomes vapor, or simply there exists water and vapor. That is, liquid and gaseous forms are coexisting together. After some point, if you go any further, if you give any more energy, then again it will increase and only gaseous form will be there. So if you give heat or simply change the temperature of a system, this is how the state change graph will look like. And again, you can also go from solid directly to gaseous phase. So again, I'm not discussing it because you already know this, but simply solid to gas directly. Let's say for diamonds, if you superheat diamonds, it actually converts into vapor. It just vanishes. Or if you take camphor also, that is naphthalene or camphor, anything, it actually camphor, naphthalene, anything, it directly converts to gas. It is a solid form. When you apply heat to it, the system directly converts into gaseous form. And solid being directly converted to gaseous form is known as sublimation. It is known as sublimation. So that is known as sublimation. So again, we have just two more topics, and this particular topic is about heat transfer. That is, we studied how heat works, how heat is given to a system, but we did not study how heat is exactly transferred between two systems. So there are basically three modes of transfer. That is how you can transfer heat from one system to another, or simply between a system and a surrounding. So the three modes of heat transfer which you have already studied in your high school is conduction, convection, and radiation. So just to brief and refresh your memory, let's talk about what conduction is. Again, conduction is the mechanism of heat transfer between two adjacent parts of a body because of change in temperature. That is, if you have a steel rod and if you heat up one end, you can actually feel the heat at the other end. That is because heat is being transferred, or simply, again, heat means transfer of energy. The change in temperature actually causes heat to be exchanged between the two parts. So it is known as conduction, and it actually requires a medium, because without a medium you cannot perform conduction. It actually happens because of the temperature difference between the adjacent parts of the same body. And again, the atoms do not get transferred. When you heat here, it is not like the atoms are jumping up and going to the other side. Matter is not transferred in the mode of conduction, or simply in the mode of heat transfer using conduction. Matter is not physically moving from one place to another. It is only the temperature change that is happening between the two adjacent ends. The energy is transferred because of that particular change in temperature. And again, coming to convection, it is because of the actual motion of the molecules, or we can just simply say that heat transferred by the actual motion of matter is known as convection, and requires a medium. Obviously, it requires a medium, otherwise you can't perform this, because again, here also there is a medium, here also there requires a medium. That is, if you heat up, again here I'm just refreshing your memory. So again, if you heat up a pot of water, then the molecules at the bottom layer absorbs the energy, gets heated up, and it becomes more hot. Then these molecules will actually move to the surface, and the surface molecules will come down and get heated up, and this shuffling, reshuffling happens again. And that is how convection actually works. It is only a phenomenon that is observed in gaseous or liquid states, because in solid, matter cannot actually physically move, but in gaseous or liquid state, gas can actually, or simply the molecules can actually move from their respective places. So again, it requires a medium and only possible in liquids and gases. And finally, we have radiation. Again, it happens without a medium. Radiation just means that energy is transferred. Radiation just means that energy is just transferred through the mode of radiation, or simply as a wave, or simply you'll study in second PU as packets of energy. That is, as packets of energy. So again, as waves or forms or simply packets of energy is being transferred throughout any medium, and that is known as radiation. So it means since it happens at any particular medium, we say that it does not require a specific medium to propagate. So we can say that it happens without any medium. It is the fastest mode of heat transfer, because again, radiation coming from the sun, that is the heat radiation, or simply the electromagnetic waves coming from the sun carrying energy, is actually traveling at the speed of photons, or simply at light speed, which is the fastest method possible. So it is going to be the fastest of all. And again, all bodies with temperature, may it be the sun, may it be an incandescent bulb, may it be me or you. Since we have temperature, we will emit electromagnetic waves, or simply these radiations, as we are bodies having temperature. And thermal radiation is partly absorbed and the rest is reflected. Again, you have studied that when the sun gives out its immense radiation energy, part of that energy is reflected back to space, part is absorbed and then redistributed. So that thing also you can remember. And if you also want to remember, you can remember the black body radiation also. That is, a perfect black body emits and absorbs perfect radiation. That is, it absorbs and emits perfectly the radiation which is given to that. So that is all about convection, conduction and radiation. So one more thing is that convection can be actually categorized into two, that is natural and forced convection. So what is natural convection? That is happening naturally. Yes, that is happening naturally. So how does that particular thing happen? So natural convection again can be classified, or the examples can be given as sea breeze and land breeze. Sea breeze and land breeze. Sea breeze and land breeze. So what is sea breeze and land breeze? During the daytime, the water in the ocean is actually preferably cooler, but the land gets heated up very fast, which means that the air now, that is the gaseous medium, is now at a higher temperature compared to the lower temperature in the oceans, which means there is a temperature difference. So molecules, that is the heated up molecules from this side, rises up, creating a lower pressure region here, which means that there is a difference in temperature and automatically an air current forms from the cooler region to the hotter region, which means that then automatically an air current is formed between the sea and the land, which means that cool air from the sea now blows towards the land side. Now, this happens during the daytime. Now, what happens during the nighttime? So, again, water is cooler and sand heats up faster because the specific heat capacity of water is comparatively very higher. So, that means that during all the daytime, the heat is absorbed by the sea, that is the ocean, and during the nighttime, the water actually gets to a warmer state. And since sands cool down much more faster, we can say that this particular sand, that is the land region, now cools down while the sea region is at a higher temperature. So this process reverses and cool breeze from the land blows to the sea, and that is known as land breeze. So that is land breeze and sea breeze. So that is natural modes of convection, and there is a forced mode also. That is, you're using a mechanical pump in order to pump this particular, in order to force convection. That is known as forced convection. So how do we do that? The material is actually forced to move using a pump or a system or any other means. So that particular system or that particular means is known as forced convection. And the very easy example is your own heart. So heart is a pump that pumps blood throughout your body, giving you your heat. That is, when your heart stops or blood flow decreases, that part of your body turns cold. That is because this pump, it beats, it pumps blood, warm blood throughout your body, giving you your body heat. So that particular arrangement of the heart and the body in order to maintain that temperature equilibrium or simply homeostasis, we can say that it is an example of forced convection. You're using a pump, that is the heart, in order to pump blood, that is a liquid, throughout your system, that is your body, in order to maintain a feasible temperature. So that is forced convection. And the last topic of this particular chapter is Newton's law of cooling. So what exactly is Newton's law of cooling? So Newton's law of cooling states that if you keep a hot body in a comparatively lower temperature surrounding, then automatically the body will exchange heat with the surrounding and it will become in thermal equilibrium with the surrounding. And the speed of this particular heat transfer, that is the rate of the heat transfer, will be actually directly proportional to the temperature difference. That is, if you have a cup of coffee, which is extremely hot, let's say 100 degrees, and you're keeping it outside where the temperature surrounding it is 25 degrees Celsius, which means there is a difference of 75 degrees Celsius between the system and the surrounding. So that means that this coffee will cool down much more faster than compared to a coffee which is at, let's say, 30 degrees Celsius or let's say 80 degrees Celsius. We'll take 80 degrees Celsius. So it means that the energy transfer between the system and the surrounding is directly proportional to the temperature difference between the body and the surrounding. So the temperature difference, as huge as it gets, the heat transfer also, the rate of heat transfer also increases drastically. You'll actually perform an experiment that is known as Newton's law of cooling and plot a graph in your lab so that you can understand more about this phenomena. So again, it states that according to Newton's law of cooling, the rate of loss of heat is directly proportional to the temperature difference between the body and the surrounding. You can just imagine a coffee and the surrounding temperature. The coffee gets cooler much more faster if it is a hotter coffee. So again, after some time, it lingers around the same temperature, but before, when it was too hot, it will rapidly exchange heat and become much more cooler than before. So that same thing he observed and he just plotted it out as a law. So it states that rate of change, d by dt means rate of change of heat, that is change in heat, rate of change in heat is directly proportional to change in temperature of the body and the surrounding. And since it is loss of heat, I'm just putting a minus sign here, indicating that heat is lost. Heat is lost, so I'm putting a minus sign here. And in order to avoid the proportionality sign, I'm introducing a constant k, and we can see that we can shift the minus sign over to that side and we have Newton's law of cooling, that is dq by dt is equal to minus k Tb minus Ts. So I hope you have understood everything about this particular chapter, that is thermal properties of matter, which is a brief introduction to thermodynamics. So in the very next chapter, we'll discuss more about the thermal phenomena that await us. So until then, thank you.